Welcome everybody to the final session of Selected Topics in Mathematics Online Edition for Spring 2026. Our speaker today is Viktor Goryunov from the University of Liverpool, and his talk is second Arnold-Maslov classes and some loops in the spaces of Legendrian and Lagrangian maps of surfaces.
Okay,
Victor?
well pronounced. Yes, thank you. Thank you. First of all, I should apologize for my camera not working. I don't know, maybe it's some kind of conspiracy of my laptop or whatever else. But anyway, so I will not be showing myself. It will be only my voice which is present. Okay, anyway, so the topic today is quite different from the number theory. And so perhaps it's a bit of echo. Yeah? Is it a question or whatever? It's a bit of echo. Okay. Anyway, let me carry on. Okay. So first of all, a little bit about the terminology used in the title. So first of all, Arnold-Maslov classes. So they are indexed by natural numbers. So kth Arnold-Maslov class of a Lagrangian or Legendrian map of a manifold is due to the closure of the set of correct k points of the map. So this means that we are taking points at which the kernel of the derivative of our map is k-dimensional. Okay. Now, if we are working with Lagrangian or Legendrian maps, then the codimension of this set sigma k in the manifold, in the source manifold, will be k times k plus 1 over 2. And okay, so this means that this is an element of the corresponding cohomology class of M. Okay, so this class is integer for odd k and only mod 2 if k is even. So we are doing today the k even case, but in slightly different situation. And in our situation, the classes are going to be integer. Okay, what else? Now we are considering maps of surfaces. So this is, and for this we are also considering a second class of Arnold and Maslov. And this means that so the virtual dimension of the corresponding set sigma 2 in our surfaces is -1. So this means that we are actually looking for we'll be looking for loops in the spaces of our Lagrangian or Legendrian maps of our surface, and then we will be somehow trying to associate integers to such loops. Okay, so the values will be on loops in the spaces of maps. Okay, mostly it will be about Legendrian case, which is perhaps better visualizable, but anyway, so let's have a look how it goes in the Legendrian case. Okay, the plan for today will be perhaps as follows. So first of all, we will see what animals are France in R3 without vertical tangents. We will look at the generic singularities. We will also consider how to attach handles to the surfaces which are being mapped. And then we will also consider rank 2 bifurcations in one-parameter families of our maps. And then we will build up corresponding codimension 1 cycles in the spaces of maps. Okay. Now, after that, we will produce generating families for special Legendrian maps of oriented surfaces, and this type of examples it is constructed to show that the values of our analogs of Arnold-Maslov classes on the corresponding loops are non-trivial. Okay, and then if time permits, I will say a few words about the Lagrangian version of the same. Okay. Now, a little bit more about the vocabulary used here. We will be working in context space R5, and this will be considered as the space of one jets of functions in two variables. Okay, so and the context structure there will be given by the formula here. So it will be alpha is du minus v capital dv minus w capital dw, and here v and w are small letters are on the source of the functions, and u are values of the functions. And the capitals are coordinates along the fibers of the vibration of this projection of one jet to zero jets. So zero jets, they are just the three space V, W, U. Okay. Okay. So of course there exist general notions of context structures, of context vibrations, but of Legendrian vibrations. But so I will perhaps not go to the full generality in this settings. Okay, then maps we are doing here. So these maps are called Legendrian maps. So we are taking a compact smooth surface as a source of this map, and then we consider maps of this surface to the zero jets, which are going through the projection pi. So here we are considering the compositions pi of pi and I. So I is a Legendrian immersion of our surface to the one jets, and being Legendrian immersions means that if I pull back this contact form alpha, so this contact form alpha, I pull back against my map, so then it will be zero. So in the other words, this means the following, that, okay, I have my manifold M now sitting in the one jets, and at every point it has a tangent space, and if I consider the tangent space, then this tangent space at any point of point M, then it will be all sitting in the hypersurface alpha is zero. Let's hit. Okay, tangent. So so our manifold is our immersed manifold is everywhere tangent to the context structure. Okay, so here we are. So these are kinds of maps we are considering. Now, how can we view them? So perhaps the best illustration is to view them via what is called wavefronts. So these are images of the maps, of the Legendrian maps in the free space here. Okay, in here. And then this will be singular surfaces with, in general situation, they will have quite constrained singularities. But the major feature here is they will not have vertical tangents. Okay, so this is because the following happens. If I have Okay, so the description of a tangent to a wavefront at a point in R3, it is that so there's this form alpha, the corresponding form alpha on that should be 0. And this means that if our, for example, if our front is a graph of a function u in v small and w small, then the coefficients v capital and w capital will be derivatives of these functions, and we want there will be partial derivatives of this function, and we want these derivatives to be finite. So, and this means that we couldn't allow any vertical tangents to our wavefront. Okay, what else we can say here? These fronts are naturally framed by the choice of the direction of the line R here, U, and this framing will also be playing an important role in cooking up the cycles and everything. Okay. Okay. Now, example. There is no possibility in this situation to have, for example, a smooth sphere as a front. So if I have a smooth sphere in a three-dimensional space, and if I have also a projection sending this sphere to a plane, then I will be forced to have vertical tangents, and we prohibit such. So this is why the simplest, okay, two sphere in as a front of a Legendrian map is what is usually called a flying saucer. So here the equator is a cuspidal edge of the surface. So cuspidal means that if I have transversal section of that, then it will be the transversal section will be in local coordinates, like written like okay, u cubed is v squared, something like that. Okay. This is about if I take a transversal here to a local transversal here and have a look at the section of the flying saucer. Okay, here we are. Now, in general, if we are thinking about local singularities of Legendrian maps and of their fronts, then they may be described in terms of what is usually called generating families of hypersurfaces. So this is U, it's a function in X and Y, so this will be okay, parameters for our situation, and then we have also V and W. So these are the coordinates of what we have had in our R3, and the corresponding wave fronts will have local description as follows. Okay, so this will be a set of points in R3 for which there exists point in the space in this space of this additional variables, and in this case, so this point X and Y should be critical point for the corresponding function in X and Y, and U will be a value of this function at this point. Okay, so in other words, this is okay. This is the standard discriminant, which is usually considered in singularity theorem. Okay. So this is here. Now, okay. So what are generic singularities? of our wavefronts in R3. Of course, so this may be smooth sheets. This may be a transversal intersection of 2 or 3 smooth sheets. There may be also cuspidal edge, and as well as cuspidal edge transversally intersected by the by a smooth sheet. Also, there are 4 types of what's usually called swallowtails. So these are given by deformations of A3 functions. Okay, so it's a standard notation for singularities of simple singularities of functions. So the function is in this case is x to the 4th plus y squared. And then we have here 4 types of such swallowtails. So there are 2 options to choose the signs here. So these are black signs and red signs. The red signs is coming from the way our generating functions are constructed. So this will be signs of u here and x to the 4th on the right. So on the other hand, you can also think about A3 with red plus or minus as a graph of u is plus or minus x to the 4th, etc. Okay, so there are 2 types of singularities, real types of singularities, A3, either x to the 4th or negative of that. Okay, and so if we look at this, look at what this formula give us as surfaces as fronts in the 3 space, then it will be okay 2 surfaces like that, and then what is so this small part is usually called the pyramid, and so in the red plus case, the pyramid is on the top relative to direction of u of our of the main part of the surface, and in the negative, and when we have red minus, then it will be below. Okay. Now about the other sign, so this plus or minus here, this is the sign of the local degree of what? We have our Legendrian map, phi. So it has images like that. And then we projected these local images onto the VW plane. And this plus minus sign is local degree of the corresponding map from, okay, we have coordinates here x and y, and we are going down to v and w. So this map between two surfaces has local degree, and if we, of course, if we have chosen the orientations, and then this will be this local degree will be the black marking of the swallowtails. Here we are. Okay, this was generalities about Lagrangian maps, Legendrian maps, and now we are trying to understand how we can somehow modify our images if we have some front in the 3 space. So it's image of certain map, of certain Legendrian map, and now we'd like to modify the source of this map. Okay, and so we are going to try to attach handles to the surface which we already have. So handles in this situation, they are not like just smooth tubes, which we usually have in non-Legendrian case, but so a Legendrian tube, so the one which appears in France, it should have two edges, two cuspidal edges. Okay? And then, so modification here, attaching of handle looks like follows. So, for example, take our flying saucer. So we are now looking from the top of that. Okay? And so this circle is the cuspidal edge there. And then we take small neighborhoods of 2 points on the edge, the equator, and then we attach our tube. So one end here, the other end there, and this is how we are getting the torus. Okay, so toric front. Right. All right. There will be another way of attaching a handle, and this way is related to the following local modification or local removal bifurcation of a wave front. So if we have a smooth sheet, then we can generate on this smooth sheet a surface which consists of two swallowtails. If I just make a cut here in the middle, then I will have two symmetric halves, and each of the halves here is a standard swallowtail surface. Okay. Now let's have a look how we can use that. Okay. We may start with we may start, for example, with the with the flying saucer. Then the move which is described here, it arranges kind of cabin on the top of this flying saucer. Then we are trying to attach a handle to this flying saucer with the cabin. And if we are taking one of the attachments here and the other attachment there, so we're getting the surface like that. So all the solid lines here, they are cuspidal edges. And okay, so and it's not so difficult to see that. So that this will be Klein bottle, wave front of a Klein bottle. So in the corresponding 5 space, if I lift this surface to the one jets of one jet space, 5-dimensional thing, which we had before, then we will have a Klein bottle. Okay. Fine. Now another way of using these cabins is to have a different way to organize a handle. Namely, if I take a piece of my smooth piece of my surface, then arrange the two cabins, and then I can bridge these two cabins by standard standard tube in terms of standard in terms of France, then I will get something like that. Okay. So this will be now handle attached to the smooth piece of surface. Okay, then I go further, and I would like to arrange a toric front from a flying saucer. And this will be perhaps the major example of toric fronts, which will be useful later on. And so first of all, I take, flying saucer, once again, it's just a view from the top. And then at the top, I put this handle upside down, so that the handle will be now inside the flying saucer. And so actually, this arrangement of the cuspidal edges here is very much reminiscent to how we show this visible contour of over the sphere with a slim handle. Okay, so these are usually these are critical points of this image. So this is the visual contour of a sphere with a slim handle. Okay, but please mind that so here maybe half of so two of the pieces are visible to invisible, and on the other hand, all four pieces in these situations are inside. They're invisible inside the surface, the flying saucer, original flying saucer. Okay, here we are. Okay, so this will be our principal toric front for our experiments. Okay, now about the Corank to one-parameter transitions of fronts. So Corank 2, so this means that, so these are situations, most generic situations in which our Legendrian map has a point at which the differential is, so the derivative is 0. So derivative here is, we are going maps of something two-dimensional, and so this means that so this map just has these partial derivatives all at this particular point, all zeros. Okay, there are two ways where such points appear. So the standard notation in singularities, these are d4 plus or minus, and we have a transition for d4 plus. So going here, so here we have the only point at which the only Corank 2 point here, and what happens here locally that we have kind of pocket with a cuspidal edge, and then we also have a swallowtail, and during this transition, our swallowtail somehow migrates to the other side. Okay, so of course migration happens only at the small region here, and the outside it will be still the same as it has been. And then we have our direction of the u-axis, the 3 space, and we shall call this move positive when we are going from the when the movement of the swallowtail is going from the bottom to the top. Now, similarly, we have d4 minus singularities, and this time the arrangement is as follows: that basically we have something like here shown in the middle trefoil, and before the bifurcation, we have three swallowtails away from us, and after the bifurcation, these swallowtails all come to us, and so this will be our positive direction of move here, and then it's more or less visible here that here we have had a3 point with red minus marking, and there we're having this a3 red plus, and the same situation happens in the lower line. Okay. So we have these normal forms which corresponding to the red marking. And what else? We still have this sigma. So this was the black marking, and the black marking corresponds to the. It reflects the following: that so when we are considering these two bifurcations, then this degree sigma marking of our swallowtails stays the same. Okay. So we have here a formula for our bifurcations. So lambda is a parameter in these considerations. And so when lambda is 0, and we have these degenerations, and otherwise all our phrases are generic. Okay, here we are. Okay. Now we have had 4 types of swallowtails. We have now 4 types of D4 degenerations. Okay. Now, from these D4 degenerations, we are going to try and construct codimension 1 cycles in the spaces of Legendrian maps. Okay, let's go for that. So we introduce a notation for the space of our Legendrian maps. It's LFM. M is fixed smooth surface, orientable, or even oriented. So we are taking it as we are taking first taking this to R5, and then we are projecting R3. And here we have orientation of M fixed, and we have orientation of R2 fixed, and then direction of R is also fixed. Okay. Now, this space, it contains 4 hypersurfaces which correspond to, which are made up by the maps which have this D4 degenerations or types of that, which we considered on the previous page. Okay, and these are those which are there for lambda is 0. Okay. Now these surfaces are cooriented as so by the choice of the direction of by the choice of positive direction lambda, like we did on the previous page. And from this 4 cooriented surfaces, from these 4 oriented hypersurfaces, we will now construct codimension 1 cycles in the space of the Legendrian maps. Okay. Now, to go through this construction, we should consider what we have in the closure of these D4 surfaces. Hypersurfaces, yeah? Only 4 hypersurfaces. And the only thing we need to consider are mappings with a bit further degeneration in terms of D series to D5. So, and then these degenerations, they appear for generating families. Okay, if you remember, we considered so our D4 surfaces, and they had y cubed here, and now this y cubed will be allowed to vanish, and but we will have y to the 4th, and these 2 terms here is functioning in 2 variables. This is what's usually classified in singularities as a D5 function. Okay, and after this we have its deformation, and so the parameters which will be describing how d5 singularities, or mappings with d5 singularities, are sitting in the space of our Legendrian maps. So they are described. So these features are described by the choice of these two parameters lambda. Okay, and here S is okay, as like before, we had it at pairing as a sign. Okay, so it's plus or minus 1. So basically, there are two types of this generating hypersurfaces. Okay. Now, if we try to have a look how the set of maps with the D4 plus or minus singularities are sitting around maps with the D5 singularities. So for this, we are just considering what happens in this lambda 1, lambda 2 plane. So basically, this is lambda 1, lambda 2 plane for this formula. And lambda 1 must be, I guess, going to the right, and lambda 2 will be going across. And we have, in this situation, D4 minus and D4 plus singularities of strata meeting together at D5. And it turns out that those strata which are meeting at D5, they must have the same degree marking. So this sigma here. Okay. So it tells us that we have had 4 hypersurfaces. Now we are gluing together at D5 pairs of them. Okay, and this means that we are now getting 4 cycles. We are getting 2 cycles, 4-dimensional 1 cycles, in the space of our maps. And these are, just a sec. These are formed by two of the D4 hypersurfaces we have had before. Okay, and so the difference between these 2 cycles is the degree marking. Okay. Right. Okay, so we have proved a theorem that for a compact orientable surface M, the set of all elements of the space of all Legendrian maps of this surface with correct 2 points is a union of 2 corientable codimension 1 cycles. D4 plus and minus, like here. So plus and minus, this is the degree marking. Okay. Now, now we are going to consider loops in the space of our maps, and so the intersections, the intersection indices with of these loops with these 2 surfaces hypersurface will be taken as analogs of second Arnold-Maslov classes for Legendrian maps of surfaces. Here we are. Okay. Now we shall show that these core cycles are non-trivial. Okay, and so we will just give it an explicit construction of loops on this, on which the intersection numbers for which the intersection numbers with these 2 cycles are okay, just the early characteristic of the surface. Okay, so here we are. Right. Now, how we are going to organize these generating families? Okay. So let's consider a curve phi is 0 in the y and w plane. Okay. So it will be y and w, they will appear. So these are arguments which are appearing in the parameterizations by generating functions. So they will be coming later now in the families of generating functions. So we have this phi 0 curve. So we assume that this is compact, smooth curve in the plane, and that our phi small is positive at infinity. So it's the only perhaps constraint on the curve gamma here I would like to have is that it's the critical points of the coordinate functions v and w on this curve must be Morse. Okay. Now we will cook up a surface. So which way? So we will just take here double of the domain where our phi is non-positive. So basically we are adding x squared to the phi equal to 0, and we are getting double cover of the of these gray regions. Okay. So this will be our surface M. Now, if we try to translate this to the language of generating functions, okay, we have here this equation x squared plus 5 is 0, equation of M. We consider this as an equation derivative of f with respect to y is 0 for generating family in x, y, v, and w. Okay. So this will be related to this to the coordinates in the phi space. Okay, so then we have this being derivative with respect to y. Then the easiest way to integrate is to write we integrate x squared, we get x squared y. Then so we integrate phi small and with respect to y and get phi capital. And also we would like to introduce this other letter which we have had here. So this will be v, and this will come with x. Okay. Now, what else would we like to have here? So we have been considering loops, or at least we're ready to consider loops in the space of maps. And let's try to introduce some simple movement in these generating functions. So namely, so we will add here, introduce t. So there will be not just y, but it will be y minus t. And what we are getting here will be okay, so this family, or one parameter family of generating families of hypersurfaces. What was that? Okay. So we have here x, y, v, w, and u as well coordinates in our phi space, and t is for movement along a path in the space of maps. Okay. What else? We also have this requirement that we must have the derivative of the partial derivative with respect to x to be 0. So it looks like that. And we use this only just to have a definition of a function v on M. So because so our M, our surface M, it lived in the space of x, y, and w. And now we also need to have its last coordinates introduced as well. Okay. Now, this, by the way, tells us the following. If we take our surface M Okay, so this x squared plus phi small. And then if we take a section at y equals t, okay, then the value of v at this section will be 0. So when we fix t, so then the value of v at this section will be 0. And points with two different values of x will be glued together. Okay, so we have the line of self-intersection of our front. And it will be interval of self-intersection of our front, so it will be sitting in V0, and it will be joining to swallowtails because this is how to. So we have when we have self-intersection, it must end somewhere, and the only way to end it's swallowtails. Okay, fine. Now it also tells us the following, that if we increase our t, then the images of points of M will switch the sign of the coordinates. So at first, when t was so very, very negative, very, very negative, then so it was one sign of v for the image of the same of a fixed point, and then when t becomes very, very positive, then the sign, of course, will be changed. Okay. Now, what are special positions of the line y equals t in the YW plane? Okay, with respect to this curve and with respect to the surface, for which we will have any kind of specific bifurcations. Okay, if we have a line y equals t given there, okay, then through a critical point of function y on our curve, okay, then the corresponding bifurcation of the front will be creation or death of a cabin on the front, or maybe the hyperbolic version of a similar event. Okay. But when we are going now through critical points, line of y equals t passes through critical points of function w. Okay. Then this will be exactly the moments at which we have these default transitions of the front. It's not so difficult to see. And then, for example, if we start with an ellipse, then the situation will be as follows. Okay, so we start with an ellipse. So then first it will be, okay, sphere, it will be, okay, it will be, just a sec. It will be, so it will be a flying saucer. But then on the flying saucer, we are first introducing a cabin here. Then one of the swallowtails migrates down. Then the other swallowtails migrates down, and then there will be, as a result, a small cabin downstairs there, and then this cabin will disappear. Okay, so this line, it shows what happens with the central sections of the surfaces. So if I take the section W is constant, so somewhere in the center. Okay, so okay. Now the effect is as follows: that perhaps what you can see what happens, for example, with this point of the section. It migrated to the other side. So basically, what happened here is that we had a wavefront here, and then we considered what happens if we change the sign of V, and we change the sign of V, and this is how it goes. Okay, so change of sign of V is basically just a change of the orientation, or with the same success, we can change the orientation with a change in the sign of X on our surface M. Okay. Now, if we just try to follow the degree bifurcations here, then, okay, so we fix all the orientations in the source, and we fix the orientations in the target, okay, and then we just try to trace what kind of D4 transitions that are taking place when we are moving this line T, YST, top to the top. Then it turns out that, so with the choice of the orientations, XY on the source and VW on the target, so then at the points of minima and maxima of our function W on the surface M, we will have bifurcations D4 plus plus negative of that. Okay, and if we are doing the same by when passing through the saddle points of our surface of our function W on surface M, then here the count will be D4 plus minus. So it will be this D4 plus minus the bifurcation. So now to just a sec. Hey, come on. Okay, now to sum this up, we can say the following. So we take a path in the space of our maps for T running from negative to positive, okay, far away. And then when we count the intersection number of such a path with our cycles, D4 plus and D4 minus, then from this count we can see that there will be, with the D4 plus, it will be, the intersection number will be negative early characteristic of the surface. And with the D4 minus, it will be just 0, so it doesn't appear here in this choice of the orientations. Okay. Okay. Fine. Now we'll go back to the torus. We take a torus. We take a torus, which is coming from, okay, so I take a big circle, then I take a small hole here, and I make this small hole so that, this distance between the two curves is even smaller than this, much smaller than the size of this small hole. Okay, and then it's not so difficult to understand that the result of that the image of our Legendrian map, so the corresponding fronts for large T, so we are choosing a large value of T small, T capital, and then so for both values, very large and very large positive and very large negative, we will have the same wavefront like shown here. Okay. Perhaps the only difference there, it will be that these two fronts, they have opposite orientations. Okay. And then this means that if we try to identify So what we had with the map, the Legendrian map, which we had for positive, so very positive t small, which is okay. Take the capital here, and then with the very negative t small, so this is gamma minus t here, and then we can identify these with that composed with the orientation change of the torus. Okay, and now from this view provides us with a loop in the space of all maps, and so we have this loop. Okay, so we have this original trace, original path, then the same path, but composed with the change of the orientation, and then this will be a loop in the space of all maps. Okay, and then this means that when M is our torus, then the intersection number of these loops with both cycles are zeros. So because it should be early characteristic, which is early characteristic of torus 0. But when we go to more complicated surfaces, so we can view them as this connected sum of the same of copies of the same torus. Okay, so that's how we modify our image, our source. This is how we get the modified image, and as a result, we will have a theorem that okay, so that the intersection number of a similar loop in the space of all Legendrian maps of our surface, with each of the two d4 cycles, is exactly negative of the early characteristic. Okay. This is that. So this more or less shows that so the cycles are non-trivial, at least when the surface is not a torus, but it still have this question mark here, if maybe so both cocycles defined this way are same. Okay. So here, after this, there is of course a Legendrian case, which is pretty analogous, but perhaps I would rather prefer to hide it now, but and put a full stop here. So I guess the basic is been explained, but so Lagrangian reduction from the Legendrian is it's another pretty it's not very complicated situation. Okay, so this is that. Thank you for your attention.
Okay, so does anybody have any questions that they would like to ask? I see someone's not clap.
Okay. Okay.
Is there anything more particularly you'd like to say about this?
So there is, of course, another point to play with, maybe with the same generated families. So I don't think that I have come across any reasonable examples of generated families and construction of corresponding loops or whatever in terms of generating functions in this kind of activity about maps, Legendrian maps of surfaces. Okay, Legendrian, Lagrangian. So more or less, so the one-dimensional case is been quite a lot of work about, and so more or less it's a standard situation and known now. But so surfaces, they are, I wouldn't say that they have been sufficiently well understood from the singularity point of view. Now it's one of the attempts. So it's one of the attempts of introducing what's usually called Vassiliev type invariant of order 1. Okay.
Thanks, Victor.
Okay, you're welcome.
Well, thank you everybody for coming. I will stop the recording now.
Okay,
And...
Dirk, sorry, I'm hiding. Okay, yes. Okay, thank you.
And I'll see you all next semester.
Thank you.
Excellent, Victor.
Thank you.
Thank you, Victor.
Thank you.